So good morning, everybody. So we shall continue our discussion on sound wave propagation. Yesterday we were discussing about reflection and refraction of sound waves. It is very similar to light reflection, refraction. However, these relations that R1 minus R2 by R1 plus R2 whole square. So this thing I told that this we will derive today. So today we will make that derivation before going to several other examples of the applications of ultrasonic so two-dimensional reflection of plane waves in general, though we will restrict here mainly the sound wave. So as we have seen, the equation for sound wave is given by the equation of wave propagation. Is given by 1 by c square del square phi del t square is equal to del square phi. So this is basically the spatial gradient, and this is of course the temporal rate of change of the velocity potential of the potential. C is the sound speed. For light, it is the light speed. The fluid pressure or pressure P is given by minus rho del phi del t. So now the derivation will be simpler if we take the harmonic form of the potential. So let us take the plane sinusoidal wave. Plane sinusoidal wave as phi xt is equal to phi 0 exponential of I kx minus omega t. So where x is the distance traveled and t is the time. K is the wave number. It is given by twice pi by lambda, where lambda is the wavelength. So basically here the phase function is theta is equal to kx minus omega t. So omega and omega equal to minus del theta del t. So in that, therefore the equation becomes equation can be written as in sinusoidal variation del square phi del t square is equal to minus omega square phi. Omega is equal to k into c. So now let us take that previous example. We have two medium, then reflection and refraction. So this is say theta, this is say theta 1. This has a density rho and velocity c. This is rho 1 c1. So it can be also written in terms of acoustic impedances, because acoustic impedance is expressed in terms of rho c only. This is z equal to 0, z greater than 0, z less than 0. Let the sound pressure and velocity potential or Pi is P0 exponential of Ik x sin theta minus z cos theta in the xz plane. Because k is the wave vector which is at the direction of the propagation. So therefore, if this is the direction of the propagation, and then if this one is x, this one is z, and this is x, so there will be x sin theta and z cos theta will be involved along the direction of the propagation. And velocity potential, that is phi I p0 by omega into rho exponential of Ik x sin theta minus z cos theta. So on the same side, we have the reflected wave PR is say R is the reflection coefficient exponential of Ik x sin theta plus z cos theta, because this direction of the wave vector for this reflection is towards this positive z side, so therefore it is plus z cos theta. Sorry. So the total pressure and potential for the positive z side P is equal to P0 into exponential of Ik x sin theta minus z cos theta plus R exponential of Ik x sin theta plus z cos theta. and phi is equal to minus I P0 by rho omega exponential of I k x sin theta minus z cos theta plus r exponential of I k x sin theta plus z cos theta. This is simply taking the components of the pressure along that x component is projected along k and z component is also projected along k. So that way this x sin theta and z cos theta terms have come up. Now for z less than 0, that is the lower medium. The transmitted wave has the pressure P1, transmission coefficient is T, P0 exponential of IK1 x sin theta 1 minus z cosine theta 1, because that is minus z, always z cosine theta 1. And potential phi 1 is minus I P0 by rho 1 omega t exponential of IK1 x sin theta 1 minus z cosine theta 1. So now the key thing to equate these two terms, because the energy need to be conserved, also the potentials and the pressure along the boundary. So along the interface, z equal to 0, the continuity of pressure and normal velocity need to be maintained. So P equal to P1 and at Z equal to P equal to P1 at Z equal to 0 and omega equal to omega 1 at Z equal to 0. So therefore P0 we put Z equal to 0 in the above relation. I k x sin theta plus r exponential of I k x sin theta is equal to t p0 exponential of I k1 x sin theta 1. So that is for all x. This is for all x. That is towards the horizontal direction is basically x. This is z equal to 0, so this is z and this is x. So to equate this, we have to have k sin theta is equal to k1 sin theta 1. Because those are the oscillatory components k therefore we must have k sin theta is equal to k1 sin theta 1 and 1 plus r equal to t. Now k sin theta equal to k1 sin theta 1. This gives, if we replace k is the wave number, that is twice pi by lambda. Again lambda we can replace it by c. So sin theta by c is equal to sin theta 1 by c1. So now we had omega equal to omega 1. That is, if we apply it to the potential, that is IP0 by rho omega, is equal into minus k cosine theta exponential of ik sine theta plus rk cosine theta exponential of ik sine theta. This is equal to I P0 by rho 1 omega minus K1 cosine theta 1, that is the normal component of the velocity, are also equal. So this is the velocity component of the minus K1 cos theta 1 t exponential of ik1 sine theta 1. So this, from this it can be obtained which means 1 minus r is equal to rho k1 cosine theta 1 by rho 1k cosine theta into t. This is minus. So from these above two relations, that is one from the velocity and continuity of velocity and another from continuity of pressure, from the two continuity equations, t is equal to 2 rho 1 k cosine theta by rho k1 cosine theta 1 plus rho 1 k cosine theta. R is equal to rho 1k cosine theta minus rho k1 cosine theta 1 divided by rho 1k cos theta plus rho k1 cosine theta 1. So this is further if we replace K, so that is K and K1. So those are proportional to C and C1. So therefore 2 rho 1 C1 by rho C cosine theta 1 plus rho 1 C1 cosine theta. So this is nothing but 2 R1 cosine theta, where R1 is the acoustic impedance, or maybe we have used some R here, by R cosine theta plus R1 theta 1 plus R1 cosine theta. So this is equal to rho 1 C1 cosine theta minus rho C cosine theta 1 divided by rho 1 C1 cosine theta minus rho C cosine theta plus cosine theta 1. So this is equal to R1 cosine theta minus R cosine theta 1 divided by R1 cosine theta plus R cosine theta 1. So these are the acoustic impedances. Now for normal incidence, so R would be reflection coefficient. So this is amplitude reflection coefficient. And this is also amplitude transmission coefficient. R equal to R1 minus R divided by R1 plus R. The energy reflection coefficient will be simply R square that is square. So this way we could this relation can be proved. The reflection and transmission coefficient can be derived. The other relation that we have used yesterday, that is r equal to square root of r1 r2, and that matching thickness is equal to lambda by 4. So that also can be derived in a similar fashion, but maybe we can do it afterwards while solving some problem. That r equal to square root of r1 r2, that one whatever we have discussed last day. R equal to square root of r1 r2. So this is for the intermediate. So this can also be derived by maximizing the transmission coefficient or minimizing the reflection coefficient. So therefore, if we take the derivative of that overall reflection coefficient and transmission coefficient, that way also it can be derived. So now we shall go through the examples. Those are, one example is given. Of course, after this there is some discussion on about resonance of sound waves under some boundary conditions. So that is important in many cases because when some piezoelectric sensor or actuator is interfaced uh, to a target, then that target body act as a boundary condition, and the installation site, that the hinging site on the other side of the piezoelectric sensor, is another boundary condition. So depending on the length and the acoustic impedance of these two boundaries, actually the transmission property of the sound wave, of the sound energy, will be determined. So that has been explained by an example. Launching sound pulses into a gas. So here the transducer is fixed to a backing layer. The transducer, and here is one gas. or it could be air, but in the example there is a gas chamber. That acoustic impedance is given as 500. This is late niobate transducer. R1 is 1.6 into 10 to the power 7. This is the support layer of the backing layer, which acts not only as a support but as an acoustic absorber. So it has same acoustic impedance as the transducers, such that no reflection goes from this side to the other side. However, it has high absorption. High absorption as well. Then this matching layer would be acoustic impedance is given as R1 R2 square root of R1 R2. So that would be, so here it is 1.6 10 to the power 7 into 500. So this is 9 into 10 to the power 4. And the thickness is equal to lambda by 4. So lambda, it depends on the frequency, of course. So that depends on the frequency. For this example, what was the frequency? So it is given lambda by 4 equal to 0.25 mm. So that means the wavelength is 1 mm. So this way, the maximum power transfer can happen from the transducer to the gas chamber. Usually, of course, many other cases, generally transducer material is chosen in such a manner that the sound energy transfer would be or reflection will be minimized. Like say, if it is water instead of gas, it would be say like around, water is around I think water, how much was water? Water was around 0.4 or 0.3 into 0.13 into 10 to the power 7. Say for if it is water, for water it is 0.13 into 10 to the power 7. So for that case, if this discontinuity is small, that is lead niobate acoustic impedance is 1.6, but still we have R1 minus R is quite considerable. Now, if we use some polymer like polymer, if we use say PVDF, PVDF is how much? 0.4. PVDF is around 0.2 or something, 0.2 or 0.25, maybe 0.3 into 10 to the power 7. So therefore, even without using any matching layer, we can have a good matching if we choose proper transducer. Say for steel, we PVDF, and this one would be much less than steel. So for steel, this lead niobate will be better. Even better would be like quartz, whose acoustic impedance is higher than say lead niobate. So in that case, say quartz is quartz would be like 2 or 2, I think more or less 2 into 10 to the power 7, and whereas steel would be like 3.5 or 4 into 10 to the power 7. So in that case, those kind of transducer can be chosen.
So PBDF means?
PBDF is polyvinylidene fluoride. So it's a polymeric material. There would be some spelling mistake here. Fluoride, fluorine. Okay. So we shall discuss some other applications. Just one or two more application related to ultrasonic transducers that is given in Bentley, and maybe one or two I will take from some other book before going to ultrasound imaging. So therefore, by next week, early next week, maybe ultrasonic equipment, etc., will be, and imaging both will be covered by next week. Then after that, we will have a small test, some mock test. I will try some test in team, that is a trial test. And if it is successful, then we will have a test either in Teams itself. Otherwise, we have to register to Moodle. So that again, I have to book some slot and ask you to register in that. So that we will do if it is not successful in Teams. Okay.
Hello, sir.
Yes.
Sir, could you please repeat that part, that when impedance matching is not required?
Oh, impedance meeting is not required when the impinging medium, that is transducer, is this one. And this is the launching medium. So then the difference of these two acoustic impedances are small. So in this case, may not be required. Still we can have it, like we can have some fluid, water-like fluid, whose acoustic impedance is in between these two match like epoxy. We can use epoxy in between, but even without matching layer, we have this discontinuity quite low, because ultimately energy reflection coefficient is square of the difference. So because it is square of the difference, so it will be still lesser.
Okay, sir.